Hello there. This is the first lecture about R programming for the course ACTL1101 Introduction to Actuarial Studies. So here in this part of the course, we learn to code in this programming language called R. This is the very first lecture, so it's an introduction. And so before I jump into the content, let me explain a few things about, workflow. First of all, what you're seeing here is what you would see in ED, the platform we use. So you would have found this video under video lecture, and now I'm showing the slides, which is, well, slides of the content I'm going to present in this video. The other things you see are in the other tabs here, lab exercise space. So this is a space for you to actually try the commands I'm going to show you as you go along. Now, I know for many of you, programming is maybe new. Maybe you've never programmed in your life, which is totally fine. And so I want this to be as interactive as possible. I really encourage you, as you listen to this video and I show you different commands, you can try them out in this space. And note that you don't have anything to install, that this already works. Underneath this Ed platform, there's already coding that allows you to run your R code. In real life, when you code, you're not going to code out of this platform Ed. You're going to use the actual software R, and probably you're going to use an editor such as RStudio, which is, I think, by far the most common editor to run R code. So soon enough, I'm going to go over this installing R and RStudio. You can actually do it already. If you want to install R and RStudio on your own devices, you can do that. It's very straightforward. You follow the steps here. By the way, this is not my steps. I've embedded a web page I found somewhere else that I found has pretty detailed instructions about how to install R and RStudio. So you can follow this along to install them on your devices. But for now, you don't have to. If you just want to follow this video and try the commands as you go along, again, it's going to work in this exercise space. What I mean is simply any R command, you can type them here. For example, let's try something super simple, maybe 50 divided by 3. So I've typed my first line of code. How exciting. Now I can run it and see what the result will be. So I type or I click run here. And then in this thing called the console, I have the result of executing this line of code. And again, I did not need to install anything. It already works. Now, just note one thing, that this line here, first exercise, goes here. I can delete it. It's not doing anything. It's just a comment. So anything in R that starts with hashtag, it's not an executable line of code. It's just a comment to help readability. So again, for example, if I put in front of the second line here, hashtag, now this is not going to do anything. If I run it, nothing displays because I've made my mathematical operation here a comment. It's not doing anything. Okay, so this is my my overall comments. And the other things you will see here are to test your knowledge. So again, as I go through this content today, I encourage you to pause the videos whenever there's a small exercise and actually try it out. You can try it out here. But also at the end of the lecture, once you've become familiar with many different concepts, you can test your knowledge via this quiz here. What is called a quiz simply means that, okay, I've actually given you the answer here, but okay, this would be let's try again. 4 would be the correct answer for this very simple first question here. It's kind of a, well, you're gonna see straight away if you have the correct answer. So it's like multiple choice or short numerical things here. But now if you go here, it's more like things that you can execute. And so again, you have the exercise here and you can try it out there. And then you're not going to get like, you're not going to know if is the right answer because it's not like a multiple choice, but you can check here a solution in case you want to double check your work against like the pre-prepared template of solution. And you have other homework exercises here that you can try. And then the last thing I'm going to say is this content is I suppose self-taught, meaning I'm not going to teach that in the live lecture. You're responsible to watch those videos and then to try the exercise to make sure you understand. But I don't want you to feel that you're alone learning this. So whenever you have questions about the R content, please feel free to ask your questions on the discussion board. So in Ed, you figured out by now, I'm sure, that there's this discussion thing, which is where you can ask question. And I just want to point out explicitly that you can actually put chunks of code in your Ed question. So for example, if I want to ask a question and I want to actually put some R code there, I can, and this code will be executable by me and by you and by everybody. Let's just make more specific what I mean. Here you have code snippet. So if I click here, I can actually put a line of code that I can run. So if I, for example, want to generate random variables, so I could put rnorm. So this is a command to generate normal random variables, and let's say I want 10 of them. Then you see I can actually run this, and I can post that and to show to the staff member that might answer your question, what is your actual R code that you have a trouble with. So if I post this, then now everybody's going to see my code, and let's say that I see a mistake in this. Well, then I can reply with my own code that fixes the mistake. So again, I would include code snippet, and maybe you want it R norm with a mean of 10, but you haven't specified the mean argument. So I'm going to tell you, okay, you need a mean of 10 actually, right? And then I can post that. Okay, this is just a comment saying you can run R code on Ed, and you can post questions that have actual R code in them. Okay, now if I post this, actually I probably need to delete it. Otherwise, this is going to look very random to everybody on the discussion board, at least everybody not watching this video. So I'm going to delete all of this. And then we can go back to lessons where you would have found this video. Okay, now here there's a bunch of stuff that's all hidden probably for you. I'm going to make it available as I go along. But if I go to introduction, back to my slides, this is what I will present. But in fact, it's probably slightly neater that I open this page in full screen. So to do that, I'm going to go here on the web version of this content and go to full screen. And so here we go. Introduction to R. The learning outcomes for today. By the end of the topic, you should be able to do the following in R: perform basic calculations, perform relational and logical operations. Obviously, we're going to explain what we mean by that. Define some variables. Variables are objects in R, which we're going to cover. Recognize and create data of different types. Yes, we're going to see that in R, your data can be stored as different types, numeric, character, and so on. We're going to explain all of that. And then the last part will be tied to the probability content of the course. We'll see how to generate random observations. Actually, the small example I presented just now on Ed was actually that. I actually generated a random sample from the normal distribution. But we'll explain that in a bit more detail towards the end of this lecture. Now, as a note, the main reference we use for this content is this book that you can buy at the UNSW library, but in fact it's also available for free to download. So if you follow this link, let me just check that should be working. Yes, you get to this page, and provided you sign up with your UNSW credential, it should be downloadable absolutely for free. And so then this is a book that you will see is often referenced in the following slides. Whenever we say page, let me just show you an example, like page 39, well, we mean page 39 of this main reference. Okay, now a bit of motivation. Why learn R? So again, R is a programming language. There's many programming languages available. You might have heard of C++. Python is a big one on the rise these days. So here, why we learn R? Well, there's many different reasons, and I'm not going to say R is always the best language to use, but we need to start somewhere. And it was actually made by statisticians for data analysis. And in actual studies, we're very interested in data analysis, so it's kind of a good tool in our toolkit to know how to program in R, because it's especially good for data analysis. It's free, so that's a big plus. You have nothing to pay. The syntax is relatively simple. I'm not going to say it's always super simple, but compared to other languages, I think you can say it's fairly simple. It's pretty good at data visualization. That's going to be one of the topics we're going to cover probably in week 5, to create nice charts and graphs to illustrate the findings you've done, maybe after you've done some data analysis. It handles large data sets, so there's no issues with that. Well, I mean, as a comment, in Excel, for example, there's a maximum number of rows, which I believe is still around 1 million that you can have in your Excel spreadsheet. Now, you might say 1 million is a lot. For most applications, yes, but if you work for a large company that has um, um, tens of thousands or even millions of customers, well, each of them might have several transactions, and then you might have a data set with more than 1 million rows, in which case you might have trouble using Excel, for example. R can handle millions, tens of millions of observations, usually without problem. Okay, it's reasonably fast, and there's some tricks to actually boost efficiency, but they're probably more advanced than what we're going to cover in this course. So at least this is just for your information. RCPP is one sort of trick you can use to boost speed and efficiency in R, but we're not going to cover it in this course. It's used quite a lot in the actual industry and many other industries. Well, I'm not going to tell you it's the only software that is used, but I've definitely heard from past students that their employer was actually quite grateful that we taught R to them because they actually use it day to day. Now, a practical reason for you to learn R, I would say the majority of actuarial and statistical textbook that have some programming component actually use R. So for a practical reason, you're going to see R in many of your textbooks. And in fact, most actual courses at UNSW are going to be R-based, at least when there's programming to do. So really, I want to send you the message that you will encounter R a lot in your degree. So don't think that doing the bare minimum is the correct approach here and think, okay, I'm not going to hear about R after that. No. You will use R quite a lot in your second year, third year degrees. Just an example, but I was teaching earlier this year ACTL1142, and it was all R. Okay, every lecture we had some R there. So anyway, I think it's fair to say learning R properly now is an investment for the future. I mean, for the present as well. You want to maximize your grade in this course, I'm sure, but also it's going to be useful in the future if you make the effort. Okay, and then it's a programming language that's been available, it's been out for a long time, I think at least since the early 2000s, so basically more than 20 years. So there's lots and lots of resources online you can rely on to help you out when you have bugs. And of course, these days, ChatGPT is pretty damn good at helping you with your coding. Okay, now let's start with the actual content. First topic, R is a calculator. Yes, you can actually use R to make all sorts of simple or more complex mathematical calculations. A few examples here that, again, I encourage you to try out. So many mathematical functions are implemented in R. So trigonometric functions like sin, pi is actually the mathematical constant pi. So sin of 2/3 of pi should give you this number. And then this symbol hat is power. So 5 to the power 2 will give you, of course, 25. Again, this is a keyword. It's a function already implemented in R that obviously means the square root. So square root of 4, you will get 2. Log, that's a natural logarithm of 1 will give you 0. And by the way, again, I encourage you, try this out here. So you go to your lab exercise space. So what did we have? We had sin of 2 times pi divided by 3. Again, this is the code, but to execute it, you click run, and you see the result here. Then if you try something else, sin of 0 should give you 0, but sin of 1, sin of, what is it? Sin of pi over 2 should give you 1, if I remember my trigonometry. Anyway, you can try all those things. Log, logarithmic function, you give this number, that doesn't mean much, etc. Next here, you have this syntax, C. So C is a function that's very used in R. It creates a vector. I'm going to say a bit more about the vector later, but for now, a vector is simply a series well, in this case, a series of numbers. So C, 1, 2, 3, 4, 5 creates not a single number, but a whole series of numbers. You can think of vector in the way you would think of a vector in your math classes, linear algebra classes. So a vector is a series of numbers. And then you can have mathematical operations on your vector. So for example, this vector times 2 will create a vector where every single number in the vector is multiplied by the constant 2. and the result displays here. Now, by the way, in terms of display, there's always a little one here. So this is not code, it's just a display thing. So it tells you it's the first line of code. When you have several lines, of course, you're going to have 1, 2, 3, 4. That's just a display thing. Okay, exercise for you. Can you calculate the following? Of course, using R. So the cubic root of 8 and the constant e to the power 2. You can try it out, but actually this one I think you wouldn't know because I haven't told you how to find e, the constant. This one I think you can figure it out that it's a cubic root, so it should be 8 to the power of 1/3. So 8 power 1/3. Now, careful that the brackets here are important. And then here, e, the constant e, you need to use the keyword, so the already implemented function exp2. And by the way, here, for all those things that we call functions, and functions will be the topic of a future lecture, but for those functions, you need to use curly brackets, right? If you use square brackets, it won't work. So this is a syntax thing. What you put inside a function, you need to have it inside those types of brackets. Okay, let me just show you what I mean. If here you try log but square bracket, it will be an error message. Okay, this doesn't work. Oh, that's not what I wanted. Okay, now so far we haven't stored any values because when we executed those calculations, we get the result, but then the result is lost. It's not stored anywhere. But of course, you often, I mean, almost always, you want to store the results from your calculations or data manipulations. How you do this? Well, you use the so-called assignment operator. So this arrow here. So, okay, this is what I said. Our response to your request by displaying the result obtained after the evaluation, but then this result is lost. So to store values, you can use the assignment arrows, or you can also use equality. So sometimes you can do the same thing with two things or two syntax. So both work. There is a bit of a difference here. I have a preference for the arrow. Maybe this is my personal preference, but I prefer to use X arrow 1 because it's very clear what this is doing. It's putting 1 inside X, and then X becomes, well, X is an object that has value 1. And it works the other way around. So now 2 right arrow X, same thing. It's creating an object called X that stores the value 2, and then I can use it, later. But X equals 3 also works. So, maybe I'll show you in the lab exercise space what I mean. If you type whatever number 2, this is not doing much. I can run it. I'm going to get 2, but then I haven't stored this 2 anywhere. So if I want to create an object called X that has the value 2, then if I call X after that, I'm going to get 2. So let's try it first without displaying it. So now 2 is put in X, but I haven't displayed it. But then if I type X after, now I'm displaying it. So I'm going to display this. Now, by the way, here, this is a simple thing that this window in ed doesn't have any memory. So if I actually, after I've done that, if I type X, now X is not going to be anything because again, this simple window in ed doesn't have memory. When we will do this in RStudio, we'll see that it actually retains memory for as long as R is open. But for now, again, if I want to store something in X, I need to first declare it. So I'm going to put a 2 inside X, and then I'm going to display it. Okay, and this works the same. I'm going to put 3 inside X. X equals 3. So here, I'm simply saying I'm creating a new object called X that has the value 3. And you can actually one-shot store 1 into X and then display it. So let's try that. Actually, let's stay with the equal. Okay, now I'm actually displaying 3, but I've also stored 3 in X. Now I say I stored it. Now I kind of realize that it's maybe a bit confusing what I'm saying, that in add there's no memory. So I would have stored it inside X for later if I was using the real R, the real RStudio. But now I realize this window doesn't have any memory. So the point is more valid when you're going to use the real R, basically in next week, or maybe in 2 weeks. Actually, but I don't want this to be confusing. So let me open RStudio and just show you what I mean. Just quickly. Okay, while we wait that R is opening, I'm gonna take a sip in my Mr. Happy mug. Okay, now don't be scared by RStudio. I will explain everything about RStudio in a future video, but I just wanted to highlight the following. What am I trying to do? Opening a new script. Okay, so in RStudio, at least for as long as RStudio is open, my objects would be stored if I declare them using the assignment, right? So if I create X like this, so I'm putting a tree inside X, and then let me make this window a bit bigger to make sure everybody sees. Okay, so now I'm going to run this code. Okay, so again, this is my script, this is my code, but I run it inside the console. Now, unlike in add, now I have memory in the sense that if I call X again, R remembers that X is a tree. So that's just a side note. I hope I haven't confused you too much about this. Okay, back to my content. And again, we will explain RStudio, I promise, in a future lecture. For now, I want to keep things relatively simple. So, just a few more comments. There's actually more options to assign variables in R. Those are really the most standard, so you can use both. I don't really mind that you use this one or this one. I have slight preferences for the arrow. And you might ask, is there a difference between the two? Yes, but those differences are pretty subtle, and I really don't think they're going to create any sort of issues for this course. So in essence, I'm not going to present the difference between this assignment and this one. I will show you, however, just in a second that this doesn't work in exactly the same way, but there's more differences than that. So if you're interested, you can follow this link. It's just going to take you to this RStack question, exactly asking this: what's the difference between those two? But I'm not going to consider this to be really important, at least for this course. Okay, there's a trick in RStudio that there's a shortcut. Alt plus the minus sign will give you the arrow, but that's just a little trick when you want to code super fast. Okay, now a little exercise for you. Perform the following tasks. Create a variable with the name var1, whose value is the sum of 1, 2, 3, 4. Okay. Create a variable whose value is the multiplication of the constant e and the constant pi. Create a variable var3, whose value is the sum of var1 and var2. Display the value of var3. Okay, I think that's simple enough. You can try it out for yourself in your lab exercise space. Now present the solution. Now here, there's a slightly more complicated way to do the sum, which is to use the function sum that I haven't presented before. Most likely what you've done when you've done this yourself would have been this. you probably type just 1 plus 2 plus 3 plus 4, which is totally fine. And then var2 is the exp1, or e to the power 1. Well, e to the power 1 is just e. By e, I mean the mathematical constant e, then times pi. And now, just to show you that it works, like temporarily, those values have been stored. You can display var3 if you do that. So first line of code is executed. Second line, third line, I'm adding the result of var1 and var2, and then I'm calling var3. Okay, and then I'm going to see the result. Which obviously this number should be the same thing as if you just you just added this to the other one. All right, this whole thing will give you the same numerical result. Of course, 18.5 something. Yes. Okay, that should be simple enough, I hope. Okay, another exercise. This one maybe we can do together. Which of the following are valid methods of assigning x with the value 2? So again, we want to create a new object called x that I can use later, which is equal to 2. Okay, x equals 2. Do you think it works? Well, yes, that's exactly what we saw. I'm putting 2 inside x because I'm saying, okay, 2 goes in this direction, 2 goes inside x. Yeah, that should work, I think. Now this one, I'm putting x inside 2. That sounds weird, and no, it's not going to work. It's not going to work because 2 is a number in R, like it's a fixed object. You cannot change the value of 2. It would be weird if you could, right? So putting x inside 2 doesn't make any sense. That's not going to work. This direction works. I'm putting 2 inside x. Now, this one, does it work? No. Okay, no. And that's why I prefer the arrow, because you might have thought, okay, what I want to do is assign the value 2 to x, but R reads this as assigning x to the value 2, and that doesn't work because again, 2 is a fixed number in R. You cannot change it. You cannot put an x inside the 2, so this is not going to work. So again, you can use it x equals 2 this way, but you cannot put 2 equals x this way. And again, this is why I slightly prefer the assignment using the arrow. Because again, it's very clear. You're trying to put 2 inside x, meaning you declare a new object called x with the value 2. Okay, now a bit more about vectors. So vectors are a very important type of data structure in R. So a data structure, it's a way that R stores or organizes some data, some information. And the vector is especially important and fundamental in R. We will see other data structures in week 2, like matrices and data frames, but for now, let's stick with vectors. Now, a vector, you can really view it as simply a sequence of data points, but in R, they need to be all of the same type. So either all numbers or all characters, for example, or all logical values, true or false, that we're going to cover in a moment. Now, there's many different ways to create vectors in R. We've already seen the function C that produces a vector. For example, C123, well, creates a vector, which is a sequence of simply those numbers, 1, 2, 3. Very important, operations, such as mathematical operations, are performed on vectors element by element. What does that mean? Well, if I have this vector plus this vector, what does this do? It's going to element by element perform the operation plus. So 1 plus this gives you 5. So the first element of the first vector plus the first element of the second gives you 5. Then second element of the first plus second element of the second gives you 7, and etc. But this applies also to, for example, multiplications. So careful here. This vector of 3 values times this one will be element by element. So this element times this element, the result is here. The second one times the second one, result is here. And this one times this one. So it's not the linear algebra multiplication. A linear algebra multiplication of 2 vectors would be this times this plus this times this plus this times this. So this is not what this multiplication is doing. It's an element by element operation. To produce a vector, you can also use the function sequence. Keyword seq brackets. So there's a few different ways to use sequence. Two of them are given here. So sequence from 0 to 1. So those are called arguments of the function sequence. From 0 to 1 by 0.1. That's another argument called by. So this does the logical thing, I think, to start at 0 and end at 1, and every other element in the vector will be by increments of 0.1. Another way the sequence function works is using the keyword or the argument called length. So again, we're going to start our vector at 0, finish it at 20, and we want in total 5 numbers in our vector. So of course, we're going to get 0, 5, 10, 15, 20. The elements will be equally spaced. You can also simply use the colon to create vectors. So this syntax 2 colon 10 will simply create a vector of integers from 2 to 10 by increments of 1. So again, 2 colon 10 will be 2, 3 up to 10. And this behavior, that's a very kind of compact syntax that you might think is a bit limited because it only goes by integers, but if you're a bit creative, you can create sequences that have increments of whatever you want. For example, well, maybe let's show this in the exercise space. So again, 2 to 10. I'm going to make this a bit bigger. Of course, is going to have the same result as in the slides, but let's say that I want 2 to 10 by increments of 0.5. Well, if you think about it, you could have your integers that go to 20 and then divide them by 2, right? So if I go up to 20, but then I divide by 2, then it should work, right? Because the first one will be 2, but then at the end I divide by 2. So the first element will be 1. Then here the second element of this vector is 3, but I divide it by 2, so it's going to be 1.5, and so on. Now, of course, maybe I want to start it somewhere else. Maybe I want to start it at I don't know, 3, but then I would need to do a bit of arithmetic in my mind or pen and paper if it's more complicated to start the vector at 6, such that when divided by 2, I'm going to start at 3 and get this result. Maybe I want the last value here for some reason to be 10.5. So then, of course, I would need a 21 here. I think you get the idea. Okay, exercise for you. Create a vector of numbers from 4 up to 5, where the increments are by 0.3. Okay, that's direct application of the sequence function we just covered. Create a vector of numbers equally spaced from 4 to 5, where the total length is 5. Well, that's exactly what we just presented. So hopefully you agree that this is a syntax to use. What you might notice just that the behavior is that you're not necessarily going to have the last number be exactly equal to 5. If you know the difference between those two numbers is not divisible by 0.3, well, the last one you're going to get is 4.9 in this example. And here, same idea. You get the following result. Okay, now we get to the topic of relational operations. So here, I think it's really easily understood if we look at a few examples. The result of those relational operations will be true or false. And by relational, we simply mean we compare two numbers with each other, and we see which one is either big or equal, and so on. This is what we mean by relational operation. So, but again, the final result of executing those commands will be a true or false. Here, in essence, you can view this as a question. So you ask, is 3 bigger than 2? Well, the answer obviously is true. Is 2 strictly bigger than 2? Well, no. Is 2 bigger or equal to 2? Well, that's actually true, yeah, because 2 is equal to 2, so it is technically bigger or equal to 2. Is 1 equal to 1 true? Now, careful here. This relational operator, you need the equal equal. So this is a piece of syntax. You need equal equal, which makes sense because remember, equal, just one equal was already used before as an assignment. So you need something different to have the relational operator. So is 1 equal to 1? Of course, that's true. Now you have not equal. So it's really the opposite of equal. Is 1 not equal to 1? Well, that's false. Don't get confused by maybe the double negative. Is 1 not equal to 1? No, that's a false statement. And then you can also have a vector of such relational operations. So C again creates a vector, and then all the elements here won't be numbers anymore because each of these elements is true false. So 2 is bigger than 1, of course, so true. 4 is 4 bigger than 2? True, yes. Is pi equal to 3? False. Don't believe what they tell you in engineering school. Pi is not equal to 3. That's the joke, by the way. I respect engineers. I almost became an engineer myself, actually, but I suppose that's a story for another day. And then lastly here, you can have equality or in general relational operations comparing vectors. But careful about what this means. It's again element by element comparison. So this vector equals this vector. We're comparing this element with this element. So the first element of the first vector, is it equal to this one? Well, yes, true. Is this one, second element, equal to this one, second element of the second vector? No, that's false. And then the last one is equal. I say be careful because we're not asking, is this whole vector equal to this whole vector? Because then the answer would be just one single false. That's not what R is doing. It's again comparing element by element. Okay, now we get to logical operations. And in essence, the logical operations are the well, yeah, the and, or, and not. So let's present them in order. Again, the result will be a logical value, but now we're not asking the question big or equal and things like that. We're asking the question, for example, and. So is the first statement and the second statement true? I think you know that for a statement and another statement to be true, you need both statements to be true. But so in general, we have statement 1, and this is already a true or false. You have statement 2, that's already a true or false. But then you have this operator, for example, and. Now you're asking the question, is this whole thing true? And again, for this whole thing to be true, you would need this to be true and this to be true. Otherwise, the result will be false. I don't know if I have a simple example, if what I'm saying here is a bit abstract. Like, let's say this one is, I'm a lecturer. So that would be true. And then, and also, I have glasses. Okay, that would be true. So is the statement, I'm a lecturer and I have glasses, true? Yes. So the whole thing would output true. But now, let's say that the first statement is still, I'm a lecturer, so it would be true. And the second one is, I don't know, I'm a woman. That's false. So then the whole thing, is the whole thing true? I'm a lecturer and I'm a woman. No, that's false. So the whole thing will be false. Okay, this is just an example, but now we're going to have a look how this works in R. Okay, this is what I just explained. Now, the operator and in R has the syntax, this symbol, ampersand. But there's another one, ampersand, ampersand. So I'm going to explain the difference, but we start with ampersand. Ampersand you can use it to compare vectors. So it's again an element by element comparison. So again, this is all a bit abstract. So I think we'll understand easily when we present the example. In words, again, it compares the first element of the first vector to the first element of the second vector, then the second element of the first vector to second of the second vector, and etc. And at the end, you get a vector of logical values. So this is the example. Yeah, you have a vector of 4 true, false, true, false, true, false. By the way, the true and R can be abbreviated by just the capital letter true, and false can be abbreviated by the capital letter F. So let's see what this does. True and true. Well, that's true. True and false. That's false. Because again, when you compare two logical values by and, both need to be true to output a true. And then false and true, that's false again. And then false and false, that should be false. Now here, that was kind of here we already put true and false in a vector to make it simple, but obviously you can combine what we've done in the previous section of relational operations to what we're doing here with those logical operators. Meaning, now I'm creating a vector as I did before of true false. So 2 bigger than 1, that's true, and 4 bigger than 2, that's true. But now I link it with the logical operator and to another vector which is, sorry, I got interrupted for a second. Okay, so you compare this to the vector 1 bigger than 2. Now that's and pi bigger or equal to 3. So obviously that's false and that's true. So then when you compare this to this one, you will get a true, but because this one is false, here you get a false. Hope that's clear enough. Okay, now we get to the distinction between 1 ampersand and 2 ampersands. So ampersand is again also means and. It's called a short circuit evaluation, and I think it's fair to say it's simpler, and you can only use it on scalars, so on single numbers. So you cannot use it on vectors. So let's see what we mean. Because you use it on single numbers, in the end you get one final answer. You get one final value, true or false. And usually we prefer it when we do control flows, which is what we're going to explain in week 3. But for now, let's explain the distinction. This is not a vector; it's a single value, true. Now, true and false and true. Well, the result will be false, because already true and false. This will be false, because again, you need only trues when you use and to get a true. Now let's look at this one. This is true. And this is true, and this is true. The result is true. But you see here the distinction. That's not a vector. That's a single statement. Okay, that's a single true. That's a single true, and that's a single true. Now you can have several of them. You can have more than 2, but each of those is a single true false. It's not a vector or true false like we had here. So here we had a vector. So we were comparing this thing with this thing, and then this thing with this thing. Notice that's not what we're doing. Now we're combining 3. Yes, we're combining 3 true or false, but in the end we have only one answer. Is this true and this true and this true? Well, the answer is yes, true. Okay, and so if you actually try this, if you compare a vector, if you put a vector and this, now you get the error, because that's not the purpose of this ampersand. It should be used only on scalars. Now, what's the point? You might think. Short circuit is a bit more efficient. It's a bit more efficient because when one condition fails, then the entire condition fails, and so there's no point checking the other conditions. So in terms of efficiency, in a situation where you have scalars, not vectors, it's better to use ampersand. It's slightly more efficient. Honestly, is this going to matter for the types of things we do in this course? Probably not, but we should probably tell you the correct thing, that Yes, ampersand is a bit more efficient on scalars. Just an example. So, okay, x is a negative something, so x is -2. Now we're going to compare the logical statements x bigger than 0. Well, that's false. And square root of x is smaller than 20. Now, square root of x, square root of a minus number, square root of a negative number would give you an error in R. So you might expect that this would generate an error because square root of a negative number should be an error. But it doesn't generate an error. Why? Because of the short circuit behavior, this is already false. So you know that anything after it doesn't matter. Even if it's true, the whole thing should be false, so it returns false. Okay, that's a little bit subtle, but probably good to be aware of that. Let me make this point clear in case it isn't. Let's try the other end, the one that's not the short circuit version. So here, I try the same. Okay, I'm going to try exactly what's in the slides. So this, I haven't declared my x. My bad. So we said x should be -2, and then this should work, meaning it's not going to generate an error. I get a false. But if I don't use the ampersand, this will create an error, I believe. Well, yes. Why? Because square root of x is an error, and this thing is actually executing the whole thing. It's not stopping there. Let me just convince you that square root of x is not allowed. So that's the actual problem. Yeah, I get an error there. Okay, but this point is a little subtle. Okay, it's a little subtle. I wouldn't say it's like top priority for you to know, but we're trying to be thorough here. Okay. Okay, now after and, of course, we need to present or, but I think you know that the difference is simply that if you have one statement or another statement, as long as one of them is true, then the whole thing will be true, right? Is the statement, let's use again the same silly example, I'm a lecturer or I'm a woman, that's true, because even though the second statement is false, well, the whole thing, because there's an or between, will be true. View this as one statement. I'm a lecturer or a woman. That's true because I'm one of those things. Okay, then. Yeah, but of course we have the same thing. I don't think I'm going to insist on the distinction between the one that works on vectors and the one that works on scalars only. It's the same distinction as with the AND operator. So straight bar is the OR in R and other programming languages actually. But so let's just review this quickly. Again, it's element by element. So true or true, well, that's going to be true. True or false, that's going to be true. False or true, that's going to be true, because again, at least one of them is true. And then false or false, well, both of them are false. This is the only case you're going to get a false when you use the or operator. Okay, same thing here. I don't think I'm going to review that. Again, you get, because you use the vector one or vectorized one, you get a vector for the result. This compared to this, and this compared to this. And if you use the short circuit version, now you're going to get one single answer, because again, you read this as, is this or this or this true? Well, one of them is true at least, and so you get true. Indeed, this one is true, even though the other two all are false. Okay, lastly, the not operator is much simpler. It's just in terms of syntax, it's just the exclamation mark. And it simply inverts the result. So a true becomes a false, and a false becomes a true. I don't think I have much else to say about that. Not all this becomes false, false, true. This would be false, but then the inverse of false is true. As simple as that. Okay, there's many other functions in R that operate on logical values vectors. One that can come handy is the any or the all functions. And again, I use this word function a lot. We'll give you all the details in week 3, but for now, a function is simply view it as it does something. So you give the function something, and then it spits out the result. So for in this case, I'm asking the function any, is any of those values in this vector true? The answer is true. So as long as one of those elements is true, the function any will give me the value true. It's named any appropriately. As long as any of these values are true, by any I mean at least one, then you're going to get true. And all, I think you can guess what it does. It's asking the question, are all those values true? Obviously here, as long as you have one false, you're going to get the result false. Another thing to note is that internally, R, and I believe most programming languages, treat a true as a 1 and a false as a 0, which means that you can actually do mathematical operations on trues and false. For example, simple example here, true plus true plus true plus false will give you 3. Well, yes, because again, internally, a true is a 1, so here you're adding 3 ones together, and you're adding zeros, but adding zeros doesn't do anything. Okay, another example of that. Well, it's the same example basically, but again, if I use the function sum, I'm summing all the elements of this vector of trues or false, of course. How many trues do I have? I have 2 of them. So again, I get the answer 2. And then you can do other fancy stuff. Well, fancy, I don't know if it's fancy, but slightly more advanced stuff. So let's review this syntax, see what it does. Yeah, okay. It's worth explaining that if you have a relational operation between a vector and a scalar, that's fine. It's just comparing this number to all the ones in the vector. So it's basically asking the question, is this bigger than this? That's false. Is this bigger than this? That's false. Is this bigger than this? Yes, true. Is this bigger than this? True. So basically this whole thing, well, let's try it out. But this, to convince you that I'm not inventing stuff, this whole thing should be a vector of false, false, true, true. Yeah, let's try. Run. So yes, false, false, true, true. So then lastly, if I have false, false, true, true, if I take the sum, same behavior as here, I'm going to sum twice true, and the true is a 1, so I'm going to get 2. Now we have a new function that we haven't seen before. How exciting. It's the function mean. So same thing here, but now I'm finding not the sum, but I'm finding the proportion of truths in this whole sequence. So if I take the mean of whatever number, it computes the mean, also known as the average, but the mean of numbers that are all either 0 or 1 will give you the proportion of truths. Well, yes, because obviously there's 2 numbers that are true out of 4. So I'm summing, I'm dividing 2 by 4, I get 0.5. So 50% of those values here are true. And then what else? Okay, well, if you sum how many are true, well, you get the number of truths. So this is the number of truths. If you compare this with the relational operation bigger than 0, if that's true, well, it means that at least one of them is true. So doing this is actually equivalent to doing the function any. And same thing here. If you sum how many are true and you set equal to 3, again, this whole thing will result in a one single logical value, true or false. If it's true, it means that all of them are true. Well, because there's 3 elements here. Okay, I think that's it for this topic. Okay, now variables in R, just a few comments. We've already created variables. So when we wrote, for example, x arrow 2, we've created a variable with name x. And so the point here is that you can name your variables whatever name you like. But well, there's a few rules. You actually, those are hard rules. You need to follow them to name your variables. Let's review them. A variable name can only include alphanumerical characters, underscore, or the dot. So uh, um, letters, numbers, underscore, and dots. That's it. You're not allowed to use any other special characters like, I don't know, star or things like that in the names of your variables. Okay, case sensitive. So yes, R distinguishes between upper and lower case. A variable may not include a white space. So a name cannot contain a space, and it cannot start with a digit. So just to make clear, if I want to declare, let's say I want to declare a vector, I can call it x. I can call it x2. That's fine. And then let me just display the whole thing. I can call it x2. That's fine. Or let me just use the other way to display, which is just to type x2 here. I can call it x dot 2. That's okay. But I cannot call it 2x, for example. Okay, this is not gonna work. Okay, that's not allowed. You need to start the name of your variable with a letter. Note, use meaningful names for your variables to improve the readability of your code. Yes, and here I would say sometimes there's a bit of a trade-off. You want the name to be meaningful, to mean something that you can call it follow, but you probably don't want it to be super long that it becomes kind of cumbersome. So give it a name that's relatively brief and hopefully meaningful. You kind of know what this variable represents when you read its name. Okay, just a few comments on data types. One strength of R is its ability to organize data in a structured way. This will turn out to be very useful for lots of statistical procedures and just data analysis in general to have, well, to have some objects that are numerical, some objects that are characters, some objects that are logical. Those are, I suppose, the main data types, but there's a few more. So this is a summary table. Now, there's actually two types of numerical objects in R. The difference between both probably doesn't matter too much for us, at least, but let's still present it. So you can have a numeric type that is more precisely called a double, and you can have a numeric that is more precisely an integer. So an integer, you know very well what it is. 3, 4, 5, etc. So there's no decimal places. You can have negative integers, -1, -2, -3, etc. But a double allows you to have higher, I don't want to say higher precisions, but basically decimals. And the way R internally stores those two types, numeric double or a numeric integer, is a bit different. I don't think we're going to deal with complex numbers, but they're supported in R. 3.2i, where I is the imaginary number that you've learned in your maths extension 2, I believe. Then you have what we presented, logical values, so essentially true, false. You can have missing value. We'll give an example in a second. I'm not too sure why it's considered to be illogical, to be honest, but it's also considered to be a logical value. And this is displayed in R as NA for, I believe, not available or non-available. And then you have the character, so basically text. So those are the main data types. Okay, to figure out when you have data, sometimes it really matters if it's numerical or a character, because if it's a character, you won't be able to do mathematical operations. For example, let me just show you here. Obviously, I can have 2 plus 5, and that works like a charm. But if my 2 is stored as a character, and this would happen if I put quotation marks here, then character is supported in the sense that this is going to display, right? And I can create a variable that has name x, for example, that is storing a character. Okay, this doesn't create any problem. But then, of course, I cannot do mathematical operations on characters. So 2 plus 2, this should create an error. Well, yes, because those are non-numeric. So it matters what data type you have for the purpose of what you're trying to accomplish. And what I was saying, before my own train of thought interrupted me, is that you can use the function type of to find what is the type of a specific object in R. So for example, if I create a new object or a new variable that is storing the value 1, type of A is actually double, which is slightly interesting. By default, when you create variables that are numeric, it's going to be a double, not an integer, even though 1, in fact, is an integer. Now, if you want to create specifically an integer, you can use this function as integer. So for example, C is now as integer A. Well, A was already a 1, but it was a double. And now type of C is now an integer. Now, again, this doesn't matter too much for us, I think. But I should say the type integer takes a bit less memory to store. So if you have huge data sets, like millions of observations of something, and they're all integers, well, it makes sense to store them as integers because it's going to cost you less storage, memory storage. And I also, I'm pretty sure that the other advantage of integer is that they're never rounded. So they can never be like a rounding mistake when you add them or you manipulate them with mathematical operations. While it actually happened to me before. If you start sorting with doubles, which is actually the default, if you make, I don't know, complex calculations, sometimes there's a bit of rounding there. Like I haven't seen problems with this, like basically it never caused me a problem, but I think at some point I had something that I knew the answer was 0, like exactly 0, but somehow R in the manipulations ended me a number that was like 0.00001 or something like that. You see what I mean? If it's stored as a double, there can be some small rounding that happen at the edges. But anyway, this is more of a side note. What else? Okay, so if inside X I put true, I'm gonna get type of X logical. There's also this function. Okay, there's this function is integer, so is A an integer? False, because A was a double here. Is numeric. So again, numeric is kind of the broader category. So if it's a number, it's going to be numeric, but it can either be a double or an integer. And then, okay, this works on vectors as well. If I create B, which is whatever this number, I create a vector of logical values, so B bigger than A. That would be true, and A equals B, that would be false. What's the type of my vec? Okay, so my vec is the vector I've defined here, is going to tell me logical. Well, yes, because all the elements in this vector are logical. True, false. I'm sorry, I've been talking a lot, and I'm recovering from a cold, so I need this this bit of Milo to keep going, give me the energy. So what I said before is there's this NA data type, or I suppose, what did we call it here? We called it, okay, the display is NA, but it's actually a logical value. But what is this? It simply means missing, missing value, non-available. For example, in X, if I put a number, then NA, then 6, that's not creating an error, but then is NA, so again, that's a function in R, is NA X, it's checking, okay, is this missing NA? No, so false. But the second one, yes, it's NA, so it's missing. And I suppose we'll come back to this later, but when you analyze data in real life, very often your data sets can have missing values, which is very annoying, but you have to deal with this. And so you need to be aware of this possibility that you import some data into R, some of them might be NA, and then you need to deal with that. Normally, if you try to do some mathematical or numerical operations with some NAs, the whole result will be NA, and that's not very useful. Now, there's a reason to that. Of course, you should be alert to the fact that you have NAs in your data sets, and that's why by default you get NAs when you try mathematical operations on NA values. For example, here this vector has 2 numerical and 1 missing, 1 NA. But if you take sum, it's not going to work. It's going to give you an NA, which you probably need to know that you have NAs. Now, you can, however, still apply the sum, but you need to be explicit. So if you type sum x, which again, you're trying to sum all the values in x, if you put this argument NARM to true, I forget what NARM stands for, but it's basically telling R to ignore the NAs, then it's going to give you probably what you want, which is to sum all the values there that are actual numbers. So again, you're going to get your 9. If you try the same with mean, so again, this is the function to compute the mean or average of a series of numbers, it's going to work. But careful of the behavior here. It's going to compute the mean completely ignoring the NAs. What I mean by that is it's going to say, consider that there's only 2 numbers. So the mean of 3 and 6, you have 2 numbers, so 3 plus 6 divided by 2, that's 4.5. It's not going to consider, okay, there's 3 numbers there, so I'm going to sum them and divide them by 3. No, I think it does the logical thing, which is just to totally ignore this NA. Okay, and yeah, again, dealing with NAs, as annoying as it is, it's very important once we get to importing external data and conducting our statistical analysis. But once more about that later. Okay, then we deal with the character data type. So any information between quotation marks and can be single or double. I don't think there's a difference in R. I think they really achieve the same thing. Maybe there's some subtle differences between the two, but I don't think so. This creates a character. So if I create a new object, a new variable in R called A, I put inside it this sentence, basically this string of characters. R is my friend, and then I ask type of A, I get character. You also have this function to detect if something is a character. Oh, sorry, to say true or false if something is a character. Is character A true? Okay, an exercise for you. Let me just see what's next after that. Okay, after that's the last topic. So take a second to think about this exercise. Okay, that's a very straightforward application of the content we've seen. So type of var1 should be an integer because I've specifically created var1 to be an integer. Type of character, type of var2 is a character. Now, sometimes your data is stored as a character, but you want to convert it to a number if that's possible. You can do that. Well, I haven't presented this function, so you wouldn't know, but you can do that using, for example, as double. There's also as integer, but in general, you probably want to use double just because it allows you for decimal places. Okay, but I'm kind of missing the point of what this is saying. I'm just okay. Here, var1 was an integer. If I want to turn into a double, you can do that using as double. However, you need to reassign a value to the object. What I mean by that, as double var1 doesn't do anything. You need to specifically say, okay, var1 that before was an integer, I want it to now become a double, so you need to reassign as double var1 to var1. Okay, you could name it something else. Now, so to keep in memory var1, you could create a var whatever, var3 to be as double var1, and then you would have var1 that's integer and var3 that's a double. But here, this command is erasing the previous var1 that was an integer and replaces it with a new var1 that is now a double. But what I was doing, trying to say before, which now I hesitate to tell you that it works, but let's try in real time, is I think this will work to convert a character to a numeric, for example, double. But let's try. So we're doing things, we improvise here, which is very exciting. So I'm trying to say, okay, let's say that something is stored. Okay, I'm going to call this my number. It's stored as a character. So here, obviously, if I do my num plus 2, that's not going to work. Okay, I get an error because my num is, well, it's a character. But I'm saying, I think that if I update my num like that, my num to be, well, to be a double, my num, I take my num and I create a double because here this is just a 2. I think that's going to work, but let's try. Yes, it worked. Okay. So again, I store it first as a character, or it could be stored as a character for whatever reason. I've imported it from somewhere else. I'm not happy with that because I want to make calculations on this my num. So here I transform my num, which is a character, to a double, which is numeric, and now I can do all my favorite mathematical operations. Which is good. My num to the power 8 will be 64. No, I was way off. 256. Okay. All right. Let's go back. Okay, I think I've dealt with all of this. One last thing. I suppose that's a detail, but worth mentioning, you can create a vector made of characters. There's no problem with that, right? So if you have C, which is the character 2, and then C, whatever we had before, R is my best friend. That's going to create you a vector that has two strings of characters in it. R is best friend is my best friend. Now I'm just going to display it. Okay, a vector of 2 elements. Each of them is a string of characters. I mean, this is just a single character, and this is many characters. Okay, now last topic, which is a little bit different. Now we're gonna do some well, probability stuff, and this I suppose is tied to the more theory part of the course. I don't think you need to necessarily have watched the first theory lecture. Because well, you have already a knowledge of probability because well, you were very studious in your previous math 1151 class. But in case you're rusty with probability, maybe it makes sense to watch this after you've watched the theory lecture about probability in the lecture. But I'm still going to review this content here. So in general, what we call a random variable is well, a mathematical description of the random phenomena that we encounter in everyday life. Well, what will be the temperature tomorrow? Okay, we can have a forecast, but we don't know for sure. So you might view this as a random variable that has a certain probability to be 20 degrees or 21 degrees or so on. The example I like to use is your grade. Yes, you, student watching this, your grade in this course at the end of the semester, from my point of view at least, that's a random variable. I cannot forecast what your grade will be. It depends on lots of factors. Some of them are kind of random. Did you sleep well before the exam? Did you study well? I mean, this you control, but I don't control. So from my point of view, what grade you will get is random. I'm going to get a whole distribution of grades. And I can maybe make probability statements such as from previous years, the probability you get HD is whatever, 15%, or I don't know, I'm inventing numbers here. But you see what I mean. It's a numerical quantity, but for which we cannot predict with certainty what it's going to be, but we can make probability statements such as probability to be bigger than this number is this probability. Okay, that's a very crash course on the topic of random variables. But for now here, what we want to do in this section is one thing, use the power of the computer, or the power of R, I suppose, to generate a sample from a specific distribution, such as the one you already know and love, the normal distribution, the Poisson distribution, the binomial distribution, and so on. Now, the good news for us is that many probability distributions are implemented in R already. And there are typically 4 functions you can use for each distribution. So obviously, those 4 functions have a well, different they do different things. So let's review that for the normal distribution, which you recall is the continuous bell-shaped distribution that is symmetrical. So d norm would give you the density function evaluated at a specific value for the normal. P norm is the CDF, okay, cumulative distribution function. Q norm is the quantile function. I'll explain what this is in a second in case you haven't seen this or you're a bit rusty. And R norm is the one we're going to insist on here to generate random numbers. But let's review each of them. Well, let me just, because I had opened here the normal distribution, just to remind you, by normal distribution, I mean this. This is the density function of a standard normal distribution. Now I click this link. Okay, I hope there's nothing weird on this page, but I haven't really vetted before. You see that's the density function of a standard normal. By standard normal, we mean mean of 0 and standard deviation of 1. So the density, which usually is denoted little f of x, is the value of this curve where x is the number displayed on the x-axis. So here in my slides, I have the density of the normal at the value whatever, 1.96. Here we use the standard normal, so we specifically say mean of 0, standard deviation of 1. The density is this value. Now the density, as you might remember, it's not directly a probability, so it's a bit hard to interpret this number, but 0.58 would be at the value of, here we said 1.96, the height of this curve here at the value on the x-axis of 1.96. Okay, now I should have picked a better picture because there's actually no y-axis, but hopefully you forgive me for this. Now P norm is the cumulative, so the CDF. Then P norm at 1.96, you probably remember it means the probability to be smaller or equal to whatever that number is. So in this case, the probability to be smaller or equal to 1.96. That's quite high. Well, yes, because on the picture, 1.96 is pretty far to the right of the distribution, which means the probability to be smaller than this number is quite high. Geometrically, the probability that was 0.975 is the area under the curve if you integrate from minus infinity to 1.96. And yes, it's close to 1 because there's only a tiny fraction of the curve that's left on the right of 1.96. But again, CDF, simply the probability to be smaller or equal to the value, in this case, 1.96. Then you have Q norm, which again is the quantile function. This is, well, the inverse operation in some sense, right? So here, Q norm means, or the quantile function in general means, so its argument is a probability. So here you see this argument is not a probability, it's a value from minus infinity to infinity. This one, the argument of the quantile function needs to be a probability, so a number between 0 and 1. And it gives you the number such that the probability to be smaller or equal to that number is 0.5 in this example. So again, what number is such that the probability to be smaller than this number is 0.5? Well, the answer here is simply 0 because the normal is symmetrical around 0. So again, on this picture, we're simply saying the value 0 is the value such that the probability to be smaller or equal to 0 is 50%. Well, yes, because of course, this function is perfectly symmetrical. So you have 50% chance to be smaller than 0 and 50% chance to be bigger than 0. There's another example with Q norm. Okay, well, Q norm 0.975. Remember, this is a probability. So what's the number such that the probability to be smaller or equal to this number is 0.975? Well, it should be 1.96. Well, we already knew this from here because this is probability to be smaller than 1.96 is 0.975, which means the number such that the probability to be smaller or equal to that number is 97.5% is 1.96. There's a bit of, rounding, but not rounding, but the CDF is not exactly 0.975. So this number is not exactly 1.96. But hopefully you see the link between those two functions. And then lastly, R norm is the one that generates an actual observation from the standard normal distribution, but it's a random observation. So you see, R norm, well, let's explain the syntax. R norm 1 gives you one random observations from the standard normal, but it's a random number, which means that if you try this again, try it in your own command, I'll do the same, you're gonna get something different, right? So let's try it here. I run this, I get a random number. I do this again, I get a random number. I do this again, I get a random number. Now those numbers, they stem from the standard normal distribution, so they're not totally number in the sense that their behavior overall will be predictable. If I generate a huge number of them, I will get, as a result, on a histogram, a nice normal bell-shaped distribution, but each of them looks random because, of course, each of them individually is random. Actually, maybe what I just said now is slightly confusing, so let me prove it to you that if I generate a huge number of them, their behavior will be predictable as a whole. So I'm gonna, this maybe goes slightly beyond what I want to show today, but let's do it. If I give you the, sorry, if I plot the histogram of a large number of random normal. So let's try with moderately large. Let's try with 1,000. And again, well, by default, it's going to generate a standard normal, mean zero, standard deviation 1, so I don't need to specify any other argument. This literally is going to generate 1,000 numbers from the standard normal random variable. And this is a graphical command. I'm going to plot the histogram from that. So let's try. I get the plot here. I can actually download it as a PDF apparently, but if I open it, I get this. So you see, looks like a normal shape. Now, so this is a histogram, so it counts how many data points are between -3 and probably -2.5, -2.5 and -2, and so on. I can change the length of the brackets for those intervals. So let me try that by using breaks. I can actually type a specific number. So let's try 50 maybe. Now it's going to be a bit. There's going to be more noise because my brackets are very small. But my point here, okay, this overall looks kind of normal, but I have only 1,000. If I do it again for a large number, let's say I think we can trust R that it's going to be fine for 1 million. Even let's try 10 million. Let's be a bit ambitious. So 10 million standard normal observation breaks. I can increase the breaks to at least 100. Let's see. Okay, it took a second to do because I have 10 millions, but still, you see R is pretty fast. 10 millions straight away. Now we have a very nice, to the naked eye, it looks like almost a perfect bell-shaped function because, again, this is based on 10 million observation. My point is simply this: each random observation can be anywhere in this interval, but overall, there's way more around 0 than around -4. -4 is very rare for a standard normal random variable. So overall, I get this predictable shape, the normal distribution. Back to the slides. Now this is for the normal. Many more probability distributions are implemented in R. For instance, can you guess the exp, p binom? What do these do? Think about it. Now I went ahead of myself. I think I've already done it here. That you can generate many random variables. This is just set here. There's another example with the uniform. So the uniform is the one that between two bounds, the probability density is a constant, absolutely constant, but outside the bounds, the probability distribution is 0. Here I generate 2 of them. Here I generate 4 of them, and the bounds that I set for the uniform are 2 and 7, which means I can never have numbers outside 2 and 7, but inside 2 and 7, all outcomes are equally likely. Again, because we've done this good work of using histogram, let's use it again on the uniform here. Between 2 and 7. But now let's say that again, I'm going to have a huge sample. 1 million should be enough. So you see, you get the result. Again, this is a histogram counting in small intervals how many observations we have. But this is a computer generated, so of course I'm never going to get something smaller than 2. I'm never going to get something smaller than bigger than 7, and in between looks quite equally likely. It's still random. There's still some small random variations, but this is from a sample of here 1 million randomly generated uniforms. Okay, exercise for you. Generate 2 realization of a standard normal. Okay, should be straightforward. We just did it. Generate 1 realization of a normal random variable with mean 10 and standard deviation of 0.1. Okay, so again, this highlights a behavior of R. Some arguments have default values. So if you don't specify them, R is going to execute using those default values. This is the case of the arguments mean and standard deviation. By default, they are set at 0 and 1. So here R norm 2 again creates 2 observations from the standard normal, mean 0, standard deviation 1. But you can override this by actually specifying, no, I want a mean of 10 and I want a standard deviation of 0.1. Okay, that's the end of those slides. I think that's really enough for today. Just one last comment. Here, I don't know if this lecture was maybe a bit kind of boring because we're doing just like basic syntax. It's going to be the case. I think for the first 2 weeks, maybe we need to get the basic syntax, the basic functioning of the language out of the way. But a bit later, we're going to do things that are, I think, more interesting, maybe a bit more advanced or maybe a bit more complex than what we did today. But eventually, we're going to actually use import data into R, do some statistical analysis, do some visualization. And so bear with me. We need to do kind of the more boring stuff at the beginning of the syntax and the fundamental commands. Soon enough, should be a bit more interesting. And if you already found that this lecture was super interesting, well, great. It should be what's the saying? Only up from here. Okay, and now we have those homework. Again, those. So here you don't have the solutions. But if you go in the actual ed, again, first of all, you have a quiz, which again is kind of true false, or not true false, but like multiple choice or short numerical answer you can try for yourself. And then you have those homeworks exercises, which again, you can see the solution. I'll double check. This says hidden. For me, if I click, I see the solution. Maybe for you, it's hidden. I'll double check and make the solution available if it's not currently. Okay, so thank you so much for listening and bearing with me for this, in fact, pretty long video. Hope to see you around, maybe in a lecture. Maybe I'll see you in a next video. So again, thanks very much. See you later.